Look out over the sprawling peaks of the Adirondacks. It feels as permanent and earthbound as anything can be. But the ground beneath your feet here wasn't actually made on Earth at all. For generations, miners working these ranges have been pulling heavy iron ore directly from the bedrock. The early universe contained almost nothing but lightweight hydrogen and helium gas. For a heavy element like iron to exist in these mountains, a specific physical mechanism had to manufacture it from scratch. To figure out where local geological materials came from, we have to look up. Stars operate as immense, pressurized factories, fusing those heavy elements according to strict physical laws. It starts when a massive cloud of interstellar gas collapses. The immense weight of all that matter crushes inward, generating a gravitational force so intense it spikes the core temperature to 15 million Kelvin. At that extreme heat, individual hydrogen atoms collide with enough speed to overcome their natural repulsion. They smash together and combine to form helium, releasing a tremendous blast of energy in a process called nuclear fusion. This diagram shows the delicate balance that defines the longest phase of a star's life, the main sequence. Gravity is constantly trying to crush the star inward, while the radiation pressure from fusion pushes back outward. The star stabilizes. Because fusion requires extreme heat, a star's ability to forge heavier elements depends entirely on its starting mass. More mass means more gravity, and more gravity means a hotter core. Eventually, the core runs out of hydrogen, the outward pressure drops, gravity takes over, and the core is violently compressed. This contraction drives the internal temperature even higher. Now reaching nearly 200 million Kelvin, the core crosses a new threshold. It is hot enough to force helium atoms together, fusing them into heavier elements like carbon and oxygen. This flowchart models the divergent life cycles of stars. A star's starting mass rigidly splits its evolutionary track. Following the lower path, medium-mass stars stop here. They lack the gravitational weight to squeeze their cores hot enough to fuse carbon or oxygen. With fusion halted, these stars undergo a quiet death. They gently shed their outer gas layers to form a planetary nebula, leaving behind a small, dense white dwarf that will never reach the heat required to forge iron. A star's mass is a strict physical cap. Without the requisite weight, the causal chain stops, permanently limiting its nucleosynthesis potential. This model illustrates a high-mass star. Its massive gravity drives successive, hotter fusion stages long past carbon. The star enters a rapid cycle of exhaustion and collapse, fusing neon, magnesium, and silicon, finally arriving at a solid iron core. But iron represents an absolute physical wall. Fusing iron nuclei does not release energy. Instead, it actively absorbs it. Because iron fusion consumes energy, outward pressure instantly drops to zero. Unopposed, the star's immense gravity crushes its entire outer mass inward in seconds. The imploding material violently rebounds off the iron core, triggering a supernova. Elements heavier than iron, like gold and uranium, aren't built slowly in the core. They are forged entirely in the immense heat and pressure of this explosive shockwave. This explosion also serves as the universe's dispersal mechanism. It blasts both the core-forged elements and the newly created ultra-heavy elements deep into the surrounding interstellar space. High-mass stars, through their massive gravity and violent deaths, are the singular mechanism for creating and distributing heavy atomic building blocks necessary for solid planets. Those dispersed clouds of heavy elements drift through space for billions of years. Gravity eventually pulls this enriched dust together, causing it to accrete or clump up, to form completely new solar systems. Earth's solid structure, from its dense iron core to its rocky silicon-rich mantle, accreted entirely from this recycled stellar debris. The iron ore sitting in the bedrock of the Adirondacks is physical, tangible proof of massive stars that hit the iron ceiling and exploded long before our sun even formed. This table shows how to evaluate these concepts on your exam. You must link a star's mass to its lifespan and nucleosynthesis products. To determine an end state, look at its initial mass. A higher mass dictates iron production and a shorter lifespan. Nucleosynthesis operates through a strict one-way sequence of cause and effect. It all begins and ends with the physical weight of a star.